Greetings, sentient beings, and welcome back to Punkworks. This here is episode 14 of Project Kerbal Shed, and the final part 4 of the Beam Power Compendium. Now, right off the bat, you see this bad boy right here? This here is an ablative laser nozzle. When you're working with beam networks, it's really not that far of a stretch to, get some frickin' lasers with some frickin' rockets attached to their foreheads. Or whatever Dan said. Anyway, so what we got here is a very crude, inefficient, and poorly made setup that should not be copied. You should do this better, but this is here for data gathering. This is an experiment. This is a receiver. Really nice one for receiving in the infrared spectrum, long infrared. So it's going to receive long infrared from orbit. It's going to turn it into long infrared laser and fire it at the rocket nozzle right here. All you need to run one of these is the nozzle itself, a probe core, and maybe like a battery for the probe core. But the fuel, that's plenty of PVC. It's got like 3,000 meters per second, like this, and then you stack weight on top of it and get whatever you want, or something like that. Anyway, so a better way to do this would actually be to use a mirror. Let me see if I can find that mirror. That's not the one I'm looking for. That's not the one I'm looking for. There's a mirror around here somewhere. It would be perfect for this. I think it's this one. Yeah, double pivoted infrared mirror. So it'd actually be better to do something like this. But I couldn't get this to work. The angles and all got all weird, and I couldn't make that work, but that would actually be the better way to do it. But instead, I'm just going to do it the hard way and use a receiver and then a transmitter. Otherwise, I could just point this rocket nozzle up at the sky, and it would get beam power that way. Anyway, we're going to go ahead and do that. Okay, so let's go ahead and switch this bad boy to beamed power mode off of solar mode and activate the receiver. Up in space, we have a few satellites beaming down infrared using a few different nozzle or laser beam thingies. A couple of these have felts, the free electron laser transmitters, or maybe not felts. The diode, I think these are diode laser transmitters. And then this one right here is some kind of big ball diode laser beam thingy, which with the bigger aperture gives us a smaller spot size. A lot less spread on that same wavelength, giving us a lot more access to the power through that atmosphere. As you can see here, not that getting that much here, but getting a whole heck of a lot here in that most efficient of spot sizes and waves. Because of the spot size here, 80 meters, I would need a much bigger. It would be about that big to get more efficiency from these beam power stations, but this one right here has got the smaller spot size, 8 meters, fits very nicely right there. Okay, so that's that. Alright, so we activate our transmitter, give it the full thing. Don't worry about which way it points, it's totally fine, but it's getting about a gigawatt of power there, so about a gigawatt of power. And you'll notice if we stage our engine here and turn it on, it itself is not receiving any power. Since it's attached to this vessel, this is not acting as a transmitter for this. To solve this problem, we decouple it from the vessel, okay? And just kind of hold it there, and then turn it on, and very quickly you can see it's, well, for a moment there, was totally receiving beamed power from the laser. And it is currently, it says it's still running, but it's not producing any thrust because it's not getting any power. It's just slowly using up its reserved thermal power until it runs out. But for a moment there, you did see, or at least you might have seen, it was picking up from that laser beam before it launched this whole contraption. Alright, so before it once again flies off into the great unknown. Let's see if we can hold it steady right here. Not attached, just by itself. It is picking up from that laser beam down there. Lazy. About 8 meters away. And, it's getting full power. But let's see, how much is it actually getting? Less than a megawatt? 7 kilowatts? That doesn't seem right. Alright, so about 500 megawatts gives us that. That's getting it from out in space. Okay, that's a lot better. I had to switch nozzles there. So what I did was I switched to this here shielded multi-wavelength diode thingy. It's got an integrated beam generator. It's pretty cool. Beam that right up in there, and make sure this thing right here is set to beamed power, not solar power. Made that mistake a couple times. But yeah, turns out we're getting about 800 megawatts available. We're only using about 90, which is not going to give us any thrust. So let's go ahead and turn the throttle up and see what happens. Thrust is right here, and consumed power right there. So let's turn it up. 200 megawatts. Alright, so around 380 we get about 10 kilonewtons. Full power, about 127 kilonewtons is where we got till we exploded. Which, of course, was enough to move this thing. Now more power and a little bit better of a design, and naturally you can use that to launch things into space. Cool stuff. Right. Okay, so that got me thinking, which is a dangerous thing. Sometimes, anyway. So that got me thinking, what if, what if? So I got this here probe core, and this here ablative laser nozzle, and I've got a reactor. It's a positron antimatter reactor, right there. See? Just go ahead and zoom in on that. Yep. And there's a bunch of positrons, and yeah, a bunch of radiators, and then there's a shielded, because it's got a high temperature tolerance, diode laser transmitter. It's got an integrated diode beam generator, so just one part there to make the laser. I went for a long infrared because why not? It doesn't really matter at this point. So what we're going to do is activate that, turn up our throttle, go ahead and activate the transmitter. Its current size, it'll pump out roughly 2.5 gigawatts of the 4-ish that we have available, so should be pretty good there. Let's go ahead and do that. Let's go ahead and do that. Okay. Alright, so we activate that. Activates the nozzle. As you can see, connected to this craft, it does not have any sort of connection, but as soon as we do that, it's no longer part of the vessel. We have thrust, and it's alive! Uh-oh. Nope. Oh, you're gonna crash. Okay, well, anyway, that's what's up right there. This is silly. Let me see if I can switch vessels real quick. And yeah, we're getting about 2 gigawatts of power. And oh, we just ran out of PVC, didn't we? Yeah. All right. So I don't know how much thrust we were getting, but yeah, that's some silly business right there. What do you think? So yeah, that's how the ablative laser nozzle works. You shoot a laser at it, and it goes. That's what it does. All right, let's go ahead and Clear the debris field. All right, so yeah, laser nozzles. All right, but I guess you're here to look for lasers in space, so let's go take a look at those. Okay, all right, so that was physics, the laser drive. Do with this technology what you will. Let's take a look at something a little more shiny, shall we? Yeah, it looks shiny. All right, so shiny here is fairly simple. It's a truss. It's a computer. Well, it's an IHAL. It's a felt. Long soft X-rays. Just to let you know, it's probably better to use far hard X-rays, but for this tutorial, I'm doing long soft X-rays, just so that when you make your beam network, it's much, much better than mine. That's all. Right here, I've got the triangular solar panels scaled up to 40 meters. That makes them ginormous. Okay? Ginormous. But honestly, bigger would be better. I think 60 is the maximum size there. Alright, so we'll just go with 60. Make sure got an action group because I don't want to go through and individually turn all those on. Yeah, okay. Alright, so yeah, obviously I'm not going to fly this up into orbit. It weighs 529 tons because it's massive. But yeah. Which one is this? I think it's like shiny 19. We'll just call it 19. Maybe it's 18. Anyway, it's just going to get launched. Now, definitely not going to launch these all in rockets because, I'd have to put like a bunch of these up there. And dear viewer, I'm just not going to do that. I'm so sorry. So yeah, this we bust out the old cheat menu and we set our orbit around the sun, to somewhere like right there. And yeah, call it good. All right, so let's go ahead and point. I think radial out is the direction we want to go. Yeah, we'll go ahead and do that because the sun should be right there. Yeah, okay. So we'll do that. And we'll go ahead and activate our solar panels. Look at that. Humongous. Awesome. Good stuff. Good stuff. Now, about 1 trillion of these, and all your power requirements will be met. Getting about 850 megawatts. That'll probably go down as we activate the transmitter. So let's go ahead and do that. Transmitter's active. And waste heat. It's going to get pretty hot. But yeah, that's basically it. You just stick one of these things near the sun, and you put a transmitter on it, and you're good. And these felt, the free electron laser transmitter, the coolest thing about them, you can switch the wavelength in flight to something better than, say, long soft X-ray. You can switch it to far hard X-ray if you want. Let you go ahead and make up your mind how you would like to do those. Now, get enough of those going around a planet, or not a planet, I'm sorry, around a star, and you just start beaming all that stuff back to home base. Get your swarm on. This is tame in comparison, nowhere near anything impressive, but give you an idea. You just get a bunch of these, okay? A whole heaping bunch. As many as your computer can handle. And then, beam all that stuff back to Kerbin. See how much actually makes it back. Now, at some point, you might decide you might want to go a little bigger than what we went. So you go really, really big. You get your big, big radiators, your big, big trusses, your big, big solar panels, and you get yourself a magnetic scoop, right? Once you get yourself a magnetic scoop, attached to said magnetic scoop, you place a very lovely, where is it at? Muon catalyzed fusion reactor, okay? And a container to hold some solar wind, and a refrigerator, and of course your magnetic scoop. And what you do with that is you pump in solar wind, process it into hydrogen and helium and deuterium. You don't really need the rest. I mean, you can. I mean, helium-3 is good stuff. But you get that deuterium, because this is a good spot to collect it. 3.6 milligrams per hour of deuterium just hanging out. That's pretty cool. 63 grams of helium and 180 grams of hydrogen. So with all of that solar wind, you use it to power, oops, let's go ahead and turn that back on. Use it to power your fusion reactor. And you go with whatever gives you the most power. Proton deuterium is pretty good, but you'll run out of deuterium pretty quick. Now this proton fusion is pretty good, but it's not that high power. The CNO cycle, that's the good stuff right there. 1.3 gigawatts of power output, and consumption is 5 grams of hydrogen per hour. Okay, you're getting basically 1 gram per terawatt, or 917 gigawatts per gram, or something, almost a terawatt a gram. And we're getting, using 5 grams per hour, and we're collecting, if we look back over here, 180 grams per hour. So we're at a huge surplus, so you can afford to turn the power controls on this all the way down, so that while we're doing this, let me show you what this looks like. Zoom out a little bit. Don't need this one. Theoretical supply, we get about 1 gigawatt of power out of the laser. The fusion reactor itself wants 133 megawatts for maintenance, and this is more than supplied by the solar panels, with some to spare. So all that power that's left over gets converted into X-rays and beamed out the back using the free electron rate laser. Pretty cool stuff. And you just get a bunch of those around your sun, and then you're really using solar power, like all the solar power, except you need, a bunch of these, like 1,000 million, a billion of these guys, and then you're good. Right, so once you've got your swarm set up around your star and you're beaming all that stuff back to home base, you'll want a way to receive it and then get it down, to planet. So you throw some stuff up in, synchronous orbit, and try some different stuff out. So what we've got here is a blanket photovoltaic ultraviolet receiver, and you can see it's got a connection to quite a few power transmission stations there. A few different wavelengths going on. These in the infrared range are actually meant to beam back down to Kerbin, so just kind of ignore those. But the rest are X-rays, right there, 4 nanometers, coming from various satellites around. And I tried different nozzles out, or different transmitters out, to see what kind of spot sizes I was getting. And as you can see right here, I have a diode beam laser transmitter. Basically, I have one of these, the diode beam laser transmitters, on one of those satellites out there, beaming power back. And it gives us a spot size that is 122 meters wide, which is way too big for us to effectively collect with this power receiver right here. Okay. Meanwhile, the rest of them give me a spot size that's under 40 meters. It's between 30 and 40 meters, which fits perfectly inside of one of these squares when fully deployed. So a bunch of these out here collecting, and then retransmitting that back to planet, and we get pretty good output. So this one, 1.5 gigawatts, and then there's another one somewhere. Yeah, these two are both operating under these principles, so they're both sending about 3 gigawatts total down to the planet, but not actually that much gets through the atmosphere, so it's about 2 gigawatts. And then these two are using different wavelengths as well. So let's go ahead and switch to one of those. Okay, so for this particular satellite, which is called, this is not a relay LR. So the reason why it's LR is it's because it's transmitting in long infrared, long IR. It's got a beam generator right there attached to the big dish there. And its aperture is, I believe, 10 meters, something like that. Or, no, wait. Does it tell you on here, aperture size? Diameter, 5 meters. Aperture diameter is 5 meters, as opposed to half a meter like the diode laser that I had on earlier. And this, of course, is a double pivoted thermovoltaic receiver set to long soft X-ray, which is what I'm collecting. So if we turn this on, we see that our receiver efficiency is 45% instead of 35%. So it's a much better collector. So we have a lot more power available to us, but still only a couple hundred, or, from our best. It's a Muat 3 right there. It's giving us about 385. Shiny 18. It's giving us 274 because we made it huge. That sort of thing. So different. I experimented around with different sizes and that sort of thing, and different nozzles. So different power outputs, different wavelengths, different aperture size there to kind of give some comparisons. But from what I'm seeing, I'm really liking what I'm seeing. All right, so all that gets collected and retransmitted down to the planet in long infrared. Now, this other satellite we have is a similar construction. I've named it Relay XM because what it is doing is actually transmitting in the X-band microwave range back down to planet. And we're doing this to kind of give a comparison. So about a gigawatt down to planet. And we're going to kind of compare the microwave versus the infrared. Okie dokie then. Alright, so this receiver is set to long infrared, so that we're only going to pick up from the stationary satellites out in orbit. They're right up there, about 3,000 kilometers away. Spot size from the two half-meter diameter diode beam laser transmitters in long infrared, transmitting about a gigawatt. Spot size is about 80 meters, 78.67, 78.96, depending on their actual distance. There's rough difference of almost a kilometer, which affects our network efficiency ever so slightly, because that infrared beam, it does kind of attenuate. Now, using the domed thingy with the 5-meter diameter laser beam thingy, our spot size is 7.8 meters, meaning we are much more efficient because we're collecting it much more efficiently. Okay, so this 80-meter spot size is basically taking up this entire dish, whereas this bottom relay with its laser beam is only beaming right about there. So in total we get a few gigawatts of power that we can use from the sun, requiring no maintenance. Pretty cool. And using different receivers and transmitters, we can use different wavelengths to power vessels either on the surface, in flight, or out in space, long distances, that sort of thing. Now, as far as microwaves go, you're going to want to go bigger. A lot bigger. Like really freaking big. So let's go ahead and turn that on. If we activate our receiver here, we see that Sonoda XM transmitting at 25 millimeters in the X-band microwave range. It's got a spot size of 1.8 kilometers. Okay, our receiver diameter is only 800 meters. Only 800 meters. only 800 meters. And so, yeah, we get about 33% network efficiency through that atmosphere. But that's just from the one satellite. To really get a lot of power out of your microwaves, you're going to need a lot more of these scattered around and all connected together, or you're going to have to go much, much bigger. This 800 meters is the maximum size for this one, unless I go in and edit configuration files. However, you could go really big with one of these bad boys, the oversized microwave dish transceiver. It's pretty big, about 1.6 kilometer receiver diameter. It's a little wobbly, might have to weigh it down a little bit, but you know, also not actually facing because it tipped over. Yeah, it's a little much. So you might have to employ a little bit of engineering to figure out what's actually going on with this. But I would assume we'd probably get about 50% efficiency out of this thing if it were actually pointed at the thing with a proper facing. Yep, that didn't sound good. But yeah, I mean, just a few engineering hurdles to deal with when you're working with microwave energy. It's generally a good idea to read the user's manual, unless you start a catastrophic apocalypse there. So yeah, you know, do some experiments and see if you can figure out, you know, a better way to make that work. But in general, with a big microwave beam in orbit down to planet, you're going to need a big, giant area set aside to collect those microwaves, because that beam's going to get pretty wide. Whereas if you use a laser beam, like infrared, it'll get a lot, you know, you can make a much tighter beam. It'll be a lot more efficient. But you know, there are trade-offs as far as how you have to design the transmitters and that sort of thing. But hopefully you can use that information to, you know, construct a Dyson swarm of your own, or maybe just put a few satellites in orbit that help your power needs, and you can do cool stuff with that. Okay, so when you're ready to, you know, get down to serious business with your beam power network, another good thing that you can use it for, oh, pardon me, they were talking. Another thing you can use it for is backup power. If you watched my last video, I ran out of power. I really should turn that down, shouldn't I? I ran out of power, ran out of positrons, because I spent a bunch of time flying around Eve and running my refineries and everything, and just completely ran out of power. What I could have done is had some backup beamed power to run, you know, just a little bit extra, so I didn't use up all my positrons. So yeah, get a little bit of power out of these bad boys right here. Which of course you can use to power your warp drive and take off and explore the stars. Using, let's see if I can float up a little bit, give you a better view. Tri-alpha colliding beam fusion reactor to power this particular setup. Works pretty well to charge the warp drive. It's a little slow, but it's okay. And then of course the magneto inertial fusion engine is what we're going to use for main propulsion, and then landing engine is an Attila thruster. Pretty neat. Let's go ahead and change the control point forward. Here we go. Now, once it's in place, like, it can actually land on Minmus and then deploy a drill and scoop up spodumene. stored in that cargo container. And then there's a unit right here that we can use the processor there to do the spodumene processing to extract lithium and lithium-6, which this bad boy uses as fuel. Lithium for fuel for that, lithium-6 inside the reactor. It's pretty good stuff. And again, while landed in mining and doing all that and running the refinery, instead of using up our reactor fuel, we can use beamed power for those purposes to save and make sure that we can actually eventually get home. Okay, so the magneto inertial fusion engine, it likes to rock out about 45 kilonewtons of thrust at its normal size, using up, see how much power is it using up? Only at 17 or 18 megawatts, no big deal. It's easy peasy stuff there for it. But being an electric engine and running on lithium, it's got super high efficiency. We've got like 3,000 meters per second. And we're just going to go ahead and time accelerate towards our target. And as you can see, persistent thrust and time acceleration, we're holding our heading, we're continuing to boost thrust, still getting the animations, and we're getting closer to our target. Which, by the way, I should probably turn around so I don't actually crash into it. Yeah, that'd probably be a good idea. Not crash into the target. Go ahead and fire that maneuvering thruster to make sure we miss so we don't explode. But, yeah. Beam power networks, folks. Get with them. It's the future. Okay, I'll see you next time with some more silly business, and we'll get some other projects going on. But for now, that's it for the beam power stuff. From here, I encourage you to just explore, try stuff out. As you can see, all sorts of wacky combinations and realistic combinations are available. So, you know, kerbal that stuff out. Till next time, stay frosty. Keep playing. Have fun. Peace.